Hey everyone, welcome back to my channel. So what we're seeing right now is from timeseriesclassification.com, which is a website or a repository for papers and datasets specifically for time series classification problems. And this is a description for the dataset called asphalt pavement type. And so as you can see here, this dataset was used in the paper and donated by the authors of the paper. So this is the paper that they are talking about. Basically, this paper tries to use an algorithm that could improve the classification accuracy significantly. And one of the use case is the pavement type. For this dataset, the highest accuracy is 80.66% here, and it used LCSS, which is longest common subsequence, combined with the complexity invariant distance. But this paper was published in 2018, a year before the rocket algorithm was first introduced and 2 years before MiniRocket, the algorithm which builds on Rocket, was first introduced. So I was curious about how MiniRocket would do with this dataset, because Rocket and MiniRocket are considered as the state-of-the-art method for time series classification. And that's what we're going to do in this video. More specifically, we're going to study MiniRocket, an algorithm that we're going to use in this video, and then apply it to this dataset and see whether we can improve the accuracy. Okay, let's study together. Okay, so before we get into the detail of MiniRocket, I just want to say something about this. I said earlier in the beginning of the video that MiniRocket builds on Rocket, right? And if you wonder why I don't just use Rocket instead of MiniRocket, that's because of the code implementation. So the dataset is actually a variable length. Here I have zoomed in the website and we can see that this data is variable length, minimum 66 and maximum 2371, more than 2000. Okay, and actually, theoretically, Rocket and MiniRocket can handle variable length, but unfortunately, I don't think the implementation code for Rocket is available for unequal length of input time series. And if you see the left side here, the only algorithm available for different lengths is the MiniRocket multivariate variable. Okay, so yeah, this is a little bit sneak peek for the coding section. We're going to use this function. Okay, now let's get into the detail of MiniRocket. So MiniRocket stands for minimally random convolutional kernel transform, whereas in Rocket, we don't have that minimally word. MiniRocket tries to eliminate almost all randomness from Rocket. And MiniRocket will generate, just like Rocket, they will generate kernels, and each kernel will do a convolution operation with input time series. After doing that convolution operation, they transform. In other words, these kernels will capture features from an input time series. Even though this word transform only occurs in MiniRocket and we don't see that in Rocket, the purpose of MiniRocket and Rocket is the same, which is to transform time series to a non-time series data and use that transformed dataset to train a classifier. In the papers of MiniRocket and Rocket, they will use a linear classifier, or more specifically, ridge regression. But we will see in the coding section that we will use gradient boosting. Now let's see how MiniRocket eliminates almost all randomness from Rocket. MiniRocket can do that by fixing some hyperparameters of a kernel, or maybe we can say the properties of a kernel are fixed in MiniRocket. Now let's see the first property. The First property is the length. In Rocket, the length of a kernel could be 7, 9, or 11. But in MiniRocket, the length is fixed to be 9. So all kernels out there have the same length, which is 9. Kernels are actually a filter, or more concretely, we can think of a kernel as a vector or an array. So let's say that, yeah, this is the kernel and it has 9 elements. So I need to make 9 boxes. 3, 4, 5, 6, 7, 8, 9. Okay, this is the kernel of length 9. And each of the value that fills in these boxes are called the weight. In Rocket, the weights are normally distributed with mean 0 and variance 1. But in MiniRocket, the weights are fixed to 2 values, either alpha or beta. By default, the alpha is -1 and the beta is by default 2. Furthermore, MiniRocket takes kernels with exactly 3 beta values. So in this array here, we would see exactly 3 betas. We have 9 places and we want to order 3 values. There is 9 choose 3 ways to do that, which is 9 factorial by 6 factorial times 3 factorial. And if you can help me verify it, but it equals to 84. So we have 84 kernels. Like that's the basic configuration, okay, with length 9 and 2 value weights. Okay, and then another important detail that I think it's important to share to you guys is this. We have 3 times 2 because beta is 2, and then plus 6 times -1 because we have 6 alphas. This is the alpha, this is the beta. If we sum them up, it will become 0. And this is the important thing. Actually, the value of the beta and the alpha itself are not that important. But more importantly is that the sum of the weights need to be 0 so that we can focus on the relative magnitude. Okay, now let's move on to the third hyperparameter, or the third properties of a kernel, which is the bias. And this is the only stochastic element, the only random element in MiniRocket. Why is that? Important thing I need because to choose the bias values, we need to first randomly choose one training example. Okay, so every time we run MiniRocket, the training example chosen would be or might be different. And then from that training example, we do a convolution process with a kernel and get the convolutional output. And from that convolutional output, we pick the bias values. Okay, before I continue on with the bias discussion, I need to show you first about the convolutional output. What is a convolutional output anyway? Okay, so let's say that we have like this, an input time series that looks like the above series. It has 15 elements, and the yellow array here is the kernel. It has 9 elements and only 2 weights, either -1 or 2, and the beta values are placed like that. So in the second value, in the 8th and the 9th value. And let's say that we don't have any padding. I'll tell you later what padding is, but this is a kernel without padding. Okay, the positioning like this is without padding. Okay, so this is the first positioning. So the first element of both series of both the kernel and the input time series are matched. And so the kernel meets this subsequence, the first 9 values in this series. And then they will do a dot product. After that, the kernel will move by one value, will shift by one value, and then it will meet a new subsequence, which is this one, and then do another dot product, and the kernel will shift again. It will keep shifting until the final element, or the last element of the kernel, matches the last element of the input time series. More concretely, to do that more concretely, we will build a matrix. Actually, I already made an empty matrix so far, and if you read the paper, this is called C hat. Okay, this matrix has 9 rows and 7 columns. Not all matrix C hat has the same number of columns. Okay, but I think it should be like it, and yeah, it's very likely that the total rows of matrix C hat is always to be 9, because the length of the kernel is 9. Okay, so what we do is we multiply this part, each of the matching, and then write down the result vertically in a column. So this is the first positioning, right? So I will write the result in the first column. So it will be -10, and then 6, and then 3, and then -9. Keep going like that until 16. And then the kernel will shift by one value, right? So it will become this. This is the new subsequence. And then the multiplication happens again. So -3. So because this is the second convolution operation, we write the results in the second column. Okay, I've calculated that beforehand, and so this is the full convolutional output. Oh, sorry, I mean this is the full convolution operation. Okay, to get the convolutional output, we have to sum the columns. Okay, more formally, we multiply the matrix of ones. Sorry. What I mean is, this is called a matrix of ones transposed and then times matrix C hat. This is the formal representation, the mathematical representation. Matrix 1 transpose is basically a row matrix of 1. And the length of the matrix 1 here is the total shifts. So in other words, 7, because the kernel will shift 7 times. Okay, I've calculated the column sums earlier, and this is the convolutional output. Okay, actually it doesn't end here, but let's say that if the bias is 0, that means, well, this matrix plus 0 would be still this matrix, right? So yeah, let's say that the bias is 0, therefore this is the final convolutional output. Okay, now let's get back to the bias discussion. As I said earlier, bias values are the only random element because we have to randomly select one training element. And yeah, let's say that this is the convolution output that is obtained from this random selected training example. The next step is to take the quantiles of this convolution output. Let's say that we want to take 3 bias values out of this output. We might want to take the 25th, 50th, and the 75th quantile. Then to know how many values we want to take, that depends on the dilation. Okay, so that brings us to the next hyperparameter, which is dilation. Dilation is about how spread out the kernel is. So if we see the yellow kernel earlier, like this one, this has dilation 1 because the elements are placed next to each other. But if we want to have dilation 2, that means the kernel would look something like this. So that the input, every second element of the input time series would match the kernel. The dilation ranges in this t, and that could have several same integers. For example, 1, 1, and then 1 again, and then 1 again, and then might be 2, and then 2, and so on. The maximum value, the maximum dilation by default is 32. Okay, you can check out their paper why it's like that, but yeah, the maximum dilation is capped at 32. Okay. And now let's see the exponent here. Oh, sorry, the exponent here, I mean this one here, the exponent, the leftmost exponent should be 0. Okay. So the exponents are uniformly spaced from 0 to max. And max is defined to be this one. So it's a logarithm with base 2. L input is the length of the input, and L kernel is the length of the kernel, which is 9. So the denominator here would always be 8. Okay, so I'll change this to 0. So let's say that this is our t for now, the set t. The count of each unique integer in t would tell us how many bias values we can take per dilation. Okay, so here we have 2 unique integers in t, which is 1 and 2, and then if we make a histogram here, or sorry, not histogram, more like a bar plot. Okay, we have 4 occurrence of dilation 1, and we have 2 occurrence of dilation 2. That means for kernels with dilation 1, we want to take 4 values, 4 bias values, whereas for kernels with dilation 2, we want to take 2 values only. Now let's move on to the next hyperparameters first, which is padding. For padding, it's either yes or no. Yes or no. Okay, so half of them would have padding. Now in the configuration like this earlier, this is the convolution operation without padding. If we have a padding, that means the fifth element or the center of the kernel would match the first element of the input. That's going to be the start of the beginning of the convolution operation. And the operation would end when the center of the kernel matches the last element of the input. Okay, so if I have to draw it roughly, let's say that this is the input time series and this is the beginning, the first element and the tail of the series. And let's say that I'm going to draw the kernel in black. Let's say that this is the black kernel and the shaded black here is the center of the kernel. This is not aligned, so we have to add a 0. That means we have to pad the input time series with zeros. And we also need to pad the input at the tail of the series as well, so that when it finished, when the convolution ends, the middle would be here and all the other elements of the kernel have a matching with the input. Okay, yeah. Now let's move on to the features now. For the features in Rocket, we have 2 features, which is PPV and global max pooling. PPV is proportion of positive values. However, in MiniRocket, we only take the PPV feature. In MiniRocket drops the global max pooling because, well, it turns out it's not that important. We can still get a very high accuracy even with only 1 feature. So PPV is the proportion of positive values. Let's go back to this slide. So let's say that the bias for this particular case is 0. So this is the final convolution output. The PPV for this is 2/7, because 2 out of 7 convolution output values are positive. And this is what we store in the transformed dataset. This is the feature that we want to capture. And this convolution output would be used several times depending on how many bias values we have. Okay, now lastly, the number of kernels produced in Rocket is 10,000 by default. In MiniRocket, it's roughly 10,000. Okay, to be exact, is the multiple of 84 that is nearest to 10,000, which is 9996 kernels. Okay, this is a hyperparameter too actually, but we usually don't change this. And in the coding section, we won't change this either. We'll just leave it at like this. And because we have roughly 10,000 kernels, we have 10,000 features. Okay, so the non-time series dataset would look probably something like this. The rows are the observations and the columns are the features. So we would have 9996 columns in our transformed dataset. Again, 9996 is a multiple from 84, which is the basic total kernels from what we have earlier, because we have a kernel with a length of 9 and each element of the kernel has 2 values, and we want to take exactly 3 beta values. So yeah, we have 84 at the basic level, and then if we want to combine it with dilation values, that would create this much 10K bias and dilation actually. Okay, so yeah, that's how MiniRocket eliminates almost all randomness from Rocket. Now, the second difference between MiniRocket and Rocket is that MiniRocket is much faster. And this is actually because we have fixed some hyperparameters, so that becomes faster. But aside from that, these 4 points are how MiniRocket is faster than Rocket. First of all, MiniRocket reuses convolutional output. So this is the dilation, this is the convolution output when we have dilation 1. Right, the dilation is 1. And so when we see we see here, this is just an example. I haven't calculated whatsoever. But if we want to take 4 values because of this histogram, this bar plot, then we would have 4 convolution output. Because we would use this convolution output 4 times, we would add with a different bias value every time, and therefore have a different PPV. Now, the second way MiniRocket can speed up is by avoiding multiplication. This is because we only have 2 weight values. Okay, so to understand this, let's look again at our matrix C hat. And with this particular kernel, we have beta values on the second element and then on the 8th and the 9th element. So if we look at this matrix carefully, we would notice that the second and then the 8th and the 9th row would always be 2 times the input. So like in the second row here, it's 2 times 3 and then 2 times minus 3, and then 2 times 9, 2 times 7, and so on. So we can factor out the multiplication by multiplying the input time series by the weight values. So more concretely, we take another input time series and multiply it by 2, and then we have another input, the same input is multiplied by 2, and then we save it as one vector, and then make another vector which is the input time series times -1, and then we will use these two new input to construct the matrix C hat. And then you might think, well, we still need to do multiplication by 2 and by -1. Well, actually, in my opinion, if we want to multiply something by 2, that means we're just doing addition of that thing by itself. So it's still not a multiplication. But even if it's a multiplication, we just need to do it twice actually, for once for every weight value, and then we can use it repeatedly for constructing matrix C hat. Because let me show you this. For example, like from the third element to the seventh element, they are all -1. So from the third row until the seventh row, we see a pattern here. It's like the values are shifting. So let's see here. -1 times 15 is -15, and we do that in our first convolution operation. And then when the kernel shifts by one value, the next -1, which is this one here, will meet the same number 15. So we would do another calculation of -1 times 15, which is -15. In other words, we would have to do -1 times 15 6 times. Because let me color it differently. So 1, 2, 3, 4, 5. Oh, actually 5 depends on, because of the location of the kernel. But you got my point. Instead of calculating -1 times 15 5 times, we can just use once, put it in an array, and call it repeatedly. After we get this matrix C hat, we just need to take the column sums. So that's why MiniRocket can reduce the multiplication steps. Okay, that's the second one. The third one is do the convolution operation for all kernels almost at once. So MiniRocket will do convolution operation per dilation. So they will use the kernels with dilation 1 first, and then move on to all kernels with dilation 2, and so on. For kernels with dilation 1, the beta values can be ordered in several ways, right? So for example, the beta is here, alpha, beta, alpha, alpha, and then like this, for example. Or perhaps alpha and then beta, 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 and then the rest of the elements are alpha. So the probability of this element gets an alpha is 2/3. So if we already do the multiplication of -1 times the input at that index, that means we also already have done the multiplication of -1 by the input for the next kernel, for the lower kernel. That's why we can we can save the repetition and speed up the process. Lastly, MiniRocket computes PPV for W and minus W at the same time. Okay, to understand this, let's look back at our convolution output again. So this is the convolution output for the kernel, this yellow kernel, which we call W. If we want to get the convolution output from negative W, that means we take the negative values of the weights, which is 1 and minus 2. And we also take the negative values of the output, of the convolution output. So we would have 15 and then 39, 16, minus 17, minus 50, 16, and then 12. To get the positive value, the proportion of positive value of this new kernel, this new convolution output, is actually getting the proportion of negative value of the output that we have seen earlier. And to get the proportion of negative value from the upper kernels, let me color it differently. From here, to get the proportion of negative value, it's actually just 1 minus proportion of positive value. Because these proportions, the proportion of negative and positive values, add up to 1. So once we get the proportion of positive values, we automatically get the proportion of negative value. So I guess what the paper is trying to say is that we won't set the value for the weights to be 2 and negative 2 and 1, because that's going to be exactly the same as setting the weight values to be minus 1 and 2. So yeah, that's it for the theory section. To end this section, I want to give you the reference. If you want to read more about it, you can check out this paper, MiniRocket. Or if you want to know more about Rocket, then you can read this one. Or you can check out my video about Rocket. Okay, so here we are now in the coding section. Again, this is a multi-class classification problem with 3 classes. And we have a univariate time series. So yeah, that's our input, univariate. But the length between training examples are not the same. And so does the test examples actually. Okay, and yeah, to get the data set, we have seen the website earlier. We can just download it from the website and then use it for later. Or we can call a function called load UCRUEA dataset, and this function will get the data from that website, from timeseriesclassification.com, and yeah, get the data for us. And that's what we're going to do. So to get the train dataset only, we call the load UCRUEA dataset and then put the name of the dataset, and we have to set the split to train. If we set the split to the default value, we will get train and the test datasets. Okay, but to make it easier, I just set it like this. So for getting the test dataset, I call load UCRUEA dataset one more time and set the split the test. The X train and X test would be a pandas series, while Y train and Y test would be a NumPy array. So this is the class distribution. It's very similar. So yeah, the train test is 50-50 split of the whole dataset. And as we can see, the name or the labels of the classes are cobblestone, dirt, and flexible. The classes are imbalanced, but yeah, it's not too much. And now how we want to solve this project. So after we get the raw data, we would transform it with MiniRocket, right? And therefore we get the transform data, which are the features that are captured by the kernels generated by MiniRocket. And then we use this transform data to train a gradient boosting classifier. Okay, so we're going to use gradient boosting, and more specifically, we use LGBM as our library to classify the dataset. Since the labels are strings, cobblestone, dirt, flexible, I need to encode it into numbers. So that's why I need label encoder here. And I encode the label here. Okay. So yeah. And now let's see the input data, some of the input data at least. So the first row are the time series from cobblestone classes, and then the second one from dirt streets, and the third one is the flexible. As you can see, they don't have equal length. I mean, even among the same class, they don't have the same length. So for example, in dirt class, in the dirt street class on the second row here, the middle time series is the longest. I already set the x-axis to be the same actually. Okay, so I already set share x for all subplots. So what does this time series represent? So this is an acceleration magnitude. So like in the first plot here, subplot here, this is the acceleration magnitude when the vehicle drives on a cobblestone street. If you know about acceleration, actually acceleration is recorded in 3 axes, right? Acceleration x, y, and z. And so we actually have 3 time series, but then it's computed to generate, to get the magnitude. So the dataset that we download from timeseriesclassification.com is the magnitude. Okay, that's why we have a univariate time series. Now that we have seen the input data, let's do the transformation. Okay, so this is the core of the video, of the coding section at least. So we're using MiniRocket multivariate variable. Okay, variable here is to indicate that we have variable length. Okay, and the multivariate here is actually for multivariate time series, even though, in the documentation it says for multivariate time series input, even though we only have univariate, but yeah, I'll just, and then I set all the parameters to the default except for end jobs and random state. And that will create a MiniRocket instance. After that, we can fit it. When we fit it, it means we generate the kernels. Okay, and then when we transform, that's when the convolution operation happens. Okay, the convolution operation happens, so the kernels that have been generated shifted by one space, one value, and then create the PPV, not create, actually compute the PPV, and that's the feature that we get. Okay, so after we transform the data sets, we would have 96 features. Okay, and then the transform data would be fed into a classifier, and this is the classifier. We first create the instance, use LGBM classifier, and I use only 500 estimators. And to accommodate the class weight, since this is not a completely balanced data, I set the class weight to balanced so that LGBM can calculate the weight of the classes. Okay, after that we fit it to the transform dataset. That's why it's xtrain transform, as in line 50 here. Okay, and then predict it on the test data set. And I already create the confusion matrix for the result, and I also put the accuracy score as well. So let's see how it goes. So yeah, as you can see, the accuracy of the classification using MiniRocket has improved so much to 92%, 92.14% against 80.66% in the paper, in the original paper. So by using MiniRocket, we managed to increase the accuracy by more than 10%. This is exciting. And I guess being able to see that the classifier can perfectly identify between flexible and cobblestone street is really cool. So to get the accuracy, we should sum the diagonals and then divide it by the total observations in the test dataset, which is 1056. Okay, so that's it for today's video. In this video, we've learned a kernel-based approach to classifier time series, which is MiniRocket, and yeah, we have seen an improvement in accuracy using MiniRocket. I'll put the code in my GitHub. Thank you so much for watching. Please subscribe to my channel, Timely Time Series. Okay, so I'll see you next time. Bye-bye.